Hello everyone, this is Dr. Young, and in this video, we are going to take a closer look at hydrates and hemiacetals, which were the least stable of all of those derivatives of the carbonyl compounds we were talking about before. So if you take a look at these, right, this is in the previous video, these reversible reactions. I have a ketone here, and we have the hydrates, the hemiacetals, acetals, amines, and enamines. In this video, we are just going to be talking about the hydrates and the hemiacetals. We'll save the acetals for later, because they're the more stable ones, and we'll talk about their use as protecting groups. They're really great. And then in separate videos, we'll talk about the amines and the enamines. So hydrates, right, generally they're unstable. And if you remember from the previous video, right, we just said that you form these hydrates when you take a aldehyde or a ketone and you just expose them to water. They're going to form the amounts, their equilibrium constants kind of vary a little bit. We'll talk about that in a sec. But the idea is that they just form when you have water present. You don't need any extra special reagents. It doesn't have to be particularly acidic or basic, although that helps. So the idea, right, is that it just adds in to make your geminal diol. So if I take a look at this, I have this 2-propanone. One of the oxygens is going to stay, and then water was added in, right, so that I've got another O and an H here, right? So I've made my hydrate. There we go. So I've made my hydrate here. Right, and again, remember from the other video that these are also called geminal diols. Geminal diol, right? Because you have a diol, it's two alcohols on the same carbon, so geminal diol. And we would get the same thing for these other two. I won't use as many colors for these, but same deal. There's going to be equilibrium if you have water. In this case, you'll form OH and an OH. I won't draw. Well, I will. Why not? Just keep it consistent. Right, geminal diol, same thing for this one. So I have an OH and an OH and a chlorine. And in this case, oops, sorry, that's an H right there. And then that, right? So here would be the hydrates of these ketones and aldehydes. One thing I do want to mention, though, is that the more electron poor or the more electrophilic it is, the more hydrate you form. So I'll make a note of that over here. All right, so let's say that again. Just in general here, the more electrophilic, or in other words, the more electron poor the carbonyl is, the larger the proportion of hydrate. So ketones tend to not form that much hydrate, right? Because they're not as electrophilic as aldehydes are. Aldehydes are more electrophilic, they're more poor, so they tend to form more hydrate, right? I actually don't have the percentage of this top one up here, but we would definitely say that there is more of the ketone form than the hydrate form. It's still enough for us to do things like oxidations and stuff and for us to consider, but there tends to be more. Now, as soon as you get to acetaldehyde, which is the second one, this one probably is just about 1. This equilibrium constant is about 1. It's on the order of like 1 to 10. So it's almost 50-50 with the hydrate. And then if you have something with the chlorine here, right, since chlorine's so electronegative, it's actually making this aldehyde more electrophilic and more electron poor. And now we're going to see that you actually have more of the hydrate than you do the parent aldehyde. It's like, I think its K is somewhere around 27 or something like that. So you can have varying amounts of these. They are reversible. Generally speaking, you have more of the carbonyl form. But if you have some really reactive aldehyde, there might be more of the hydrate form of the two. Mechanism for this, pretty straightforward. Just a couple steps here. I'll use this parent ketone up here so you can see it. All right, so double bond O. I'll draw my water in blue just to help emphasize it here. So I've got my H2O. And if I put my partial charges on everything, right, partial negative on the carbonyl oxygen, partial positive on the carbon, positive on the hydrogens on the water, and a negative on the oxygen. So my first step for this, right, would just be that my oxygen is going to be attracted to the carbonyl carbon, right? This poor nucleophile here is going to attack this, which is going to give us a sort of awkward looking intermediate, where now I have an O minus, and then I have the water hanging off. And I say awkward looking intermediate, right? Because as you might imagine, it's not like you're going to have a whole bunch of this. There's not a lot of thermodynamic reasons why water would add into the carbonyl, other than the fact that, again, typically you see these when you dump these carbonyl compounds in water. So that means you have tons and tons, billions, trillions, googolplex, just some giant number of water molecules for every one aldehyde or ketone, right? So it's a numbers game. It's not a great step, but there's just so much around that you're going to get some of it, so we want to consider it. Now I've got an upset oxygen on both of these, right? I've got a negative O, which wants a hydrogen. I've got a positive oxygen, which wants to get rid of a hydrogen. So this would just be a proton transfer step here. And again, it's not like it actually probably takes it from itself, but there may be some other intermediate water molecule helping out. But what happens more or less, right, is that this one takes that hydrogen and this gets electrons back in your proton transfer step. So proton transfer. And then you formed your hydrate. Right, so now you got the hydrogen on this oxygen, you have this OH, you formed your hydrate. Bingo. Right, which is exactly kind of how I drew it up there. And that's really all it is. It's just a two-step mechanism. If you had acidic conditions, you'd protonate the carbonyl first, then have water add in. If you had basic conditions, you'd have a hydroxide attack that carbonyl and then get protonated. But neutral conditions are usually what hydrates form in, since it's just water. So hydrates are pretty unstable. Like I said, they just kind of fall apart by themselves. You don't have to do anything to make it reverse. Hemiacetals are the same way here. They're also not very stable generally. And so let me draw a couple examples of this. Right, so you might get a hemiacetal if, say, you had one equivalent of methanol. I'll put one equivalent here. Usually these have a little bit of acid around, but regardless, they're not very stable, so don't worry too much about what reagents we're going to use. But the idea is that with the hemiacetals, remember that you do form an OH, but then you form an OR, whatever the OR group was. And in my case, the OR is going to be the methyl, right? Since my alcohol has a methyl on it, this is going to be a methyl. And let me actually erase that, because that black oxygen is actually the purple one from your methanol. Right, and then you make your hemiacetal. Right, and again, hemiacetals have an OH and an OR group on them, right? So they have an ether and an OH on the same carbon. And again, these tend to not be very stable. Notice that I drew a reversible arrow. It just came right back, and it will form that. The ratios of these also vary, much like the hydrates. So the more electrophilic the carbonyl is, the larger amount of hemiacetal you probably form. But again, it's a very dynamic equilibrium. These things are not stable, and they do fall apart. It doesn't have to be a tiny alcohol. Like it could be something like, well, let's say we have isopropanol. You might imagine it goes slower because it's bigger, but it would do the same sort of thing here, right? Where you could have the isopropanol coming off of that carbon, an OH coming off of that carbon, and then that original parent CH3 here. But again, that would be the hemiacetal that you formed, right? Again, an OR and an OH attached to the same carbon. And let me just do one more example here. The most stable hemiacetals are actually intramolecular acetals, ones that sort of wrap around and attack themselves. So here what we're going to see is that if you take a look at this, let's label this carbon 1, 2, 3, 4, 5, right? What's going to end up happening here is that your carbon that has the hydroxyl group on here is attacking carbon 1 to form that hemiacetal. And so it's going to form a ring, which is actually going to make it a lot more stable and more thermodynamically favorable. Let me draw this, and I'll say another thing about that. Right, so now this is carbon 1 that got attacked, 2, 3, 4, and 5, right? Carbon 5 was the one with the oxygen. So another way to say that is that this oxygen right here, this oxygen right here is this oxygen right here, right? That's the one that attacked. So that O right there, this oxygen. And so you formed a cyclic hemiacetal, which is much more stable. Right, cyclic hemiacetal is a lot more stable, and that's just for thermodynamic reasons, right? Largely entropy. With these top two examples, you had to have a ketone flying around in a solution, right? Just randomly diffusing through a solution, and a methanol, like in that first one, also moving around in solution, and they needed to find each other, and they needed to become two pieces to form one piece. And that means you've decreased your number of possible states, so you've decreased kind of what you would call disorder, although that's a whole other can of worms I don't want to get into right now. But whenever you have two pieces becoming one piece, you've decreased the entropy of a system. So by taking two pieces and making a hemiacetal, you're actually decreasing the entropy. But if you have one molecule that has both of these reactive groups, the alcohol and the carbonyl, then you don't have the two pieces become one piece. You have one piece staying one piece. And so the change in the entropy is very, very different. You don't have two pieces becoming one piece. You have one piece and it's still one piece. So your number of states doesn't change as much. So cyclic hemiacetals are a lot more stable for that reason. It has to do with disorder. And I put under here an example as carbohydrates. You've probably all heard of glucose. A lot of carbohydrates have cyclic forms, right? So we'll talk a lot more about this later, but a lot have a straight chain form versus a cyclic form. I'll put cyclic/ring form. And so like 5 and 6 membered, if you have 5 or 6 carbons, probably going to form a ring. And but you'll notice what I want to highlight here is that this is a hemiacetal, right? So if I take a look at this, if I look over to the right-hand side, well, let me stop. If I look at glucose, I've got an aldehyde and I've clearly got a whole bunch of OHs, right? So that's exactly the recipe I need to make a hemiacetal. And if I look over on the right-hand side, here's a carbon with the OH and an OR group on it, right? So this carbon right here, this is where the hemiacetal is. And that just naturally occurs. It's not so, it's stable enough that form predominates, but it's not permanently fixed in that shape. And so you notice that again, I have the equilibrium arrows. This is beta glucose. Again, don't get too caught up in the terminology, but beta glucose would open back up to D glucose, then maybe close to alpha glucose, and maybe open back up to the straight chain, then maybe close back to beta. It's a very dynamic equilibrium, and we'll talk about mutarotation later, but here's just an example of a real life hemiacetal, and that would be a lot of your sugars, glucose, fructose, galactose, etc. So let me show you one more thing here. The mechanism for the hemiacetals, so we can take a little closer look at that. It's not that different than for the hydrates. Let me add my lone pair. I'm going to draw out my acid. Since it's a strong acid, I'm going to go ahead and split that sucker up. And I'll draw my methanol here, CH3OH, and let me draw that in a different color just to kind of emphasize it. So CH3OH with its lone pairs. And again, my carbonyl has partial charges on it, partial negative, partial positive. So my number one combo here, and by number one combo, I mean, I'm looking, I know I'm so informal sometimes with these mechanisms. What I'm looking for is the pieces with the largest charge density. So just the things that are going to be the most attracted to each other, right? So I see a bunch of partial charges. I've got partial charges on my methanol. Erase this. So partial negative, partial positive, partial positive. I've got partial charges on methanol. I've got partial charges on the ketone, but I've got a full charge on that H+. So that's probably going to be involved in my first step because it's the largest charge. It has the highest charge density. It's going to be the most attracted to a partial negative charge. And it would definitely be attracted to either the negative O on the methanol or the carbonyl. It absolutely will go onto the O in methanol, but it's just going to pop on and off. It's not really going to take us anywhere. The real first step of this, or the first productive step of this, is that it's going to protonate our carbonyl to make it look like we have a much more electrophilic carbonyl. It's going to just make it more susceptible to electrophilic attack. Right, because now this carbonyl is not going to have just a partial charge. If you look at the resonance structure, it actually has like a full charge. All right, so if you look at that resonance structure, now that carbonyl carbon actually has a full positive charge if you look at the minor contributor there. Which is great, because now that means my methanol can attack. And I don't care which drawing you use to attack that carbonyl carbon. I'm going to draw, I don't care if you do this first one, I'm going to erase it, but I don't care if you do this first one where you just have it attack the carbocation. I think that makes a ton of sense. It's like, oh, there's the electrophilic carbon, I get it, and the oxygen is going to go there. You can do that, that's totally fine. But I'm also going to erase this and show you another way you could draw this. You could also have that oxygen attack this carbon, the carbonyl carbon, which then kicks the electrons up to the oxygen so that it's no longer positive. Either way you draw the arrows, maybe you should try drawing both the arrows so that you can see that this is true. Either way you draw the arrows here, you're going to see that it leads you to the exact same product. So let me draw my next step. So now my, in this case, methanol has added. And now it's positive because that oxygen gave electrons to the carbonyl carbon. And then we have the subset O, it's positive. It doesn't want to be positive, so it's got to take electrons back from something. It's either going to take electrons back from the OC bond that it just made, which is going backwards. We are right, which is why this is reversible. Or it's going to just deprotonate. So let me see if this will catch up for me. There we go. Or it's just going to deprotonate, which is what we're going to draw because that's the step that moves forward. So I'm just going to have these electrons from the hydrogen go back onto the O, which means we've deprotonated it. We've regenerated that acid catalyst. I'm just going to fix this up a little bit, make it look a little nicer. OCH3. Plus we've regenerated an acid catalyst, right? So you don't need a lot of, like, in this case, the sulfuric acid. Right, so you regenerate an acid catalyst. That H+, that blue H+, would then go protonate another 2-propanone, then another methanol would attack it, yada, yada, yada. And if you take a look at this, right, notice that every single step, these 3 steps, they all have their reversible arrows. If you're going to talk about hemiacetal breaking down and going back into the ketone in this case, it's the exact same mechanistic steps, right? I'll draw it in red, but the idea is to start it off, what you'd do is you'd first protonate your OCH3, which would give you back this, and then it would take electrons back from there, which takes you back to there, and then you would lose an H, which means you go back to there, right? So it's the exact same mechanistic steps, just backwards is the idea. So forwards and backwards, this is a 2-for-1. Now again, these are the 2 that are not very stable, so they're not used a lot synthetically. Again, the cyclic acetals, the cyclic hemiacetals are the most stable, and you're most likely to see them with some natural products. But hydrates just kind of happen, and we just acknowledge that they happen. There's not a lot of set of reagents to, like, make a hydrate, for example. What's going to be more important is that we make and we use and we see acetals much more often. So that'll be in the next video. So go ahead and, finish up your notes and then start watching acetals, what they are, how we make them, how we use them as protecting groups. Thanks. Bye.